All right, welcome everybody to our very first FEBio webinar, an introduction to FEBio Studio. My name is Steve Moss. I am a research associate here at the University of Utah and a software developer on the FEBio and FEBio Studio projects. So let me start by giving you a brief overview of what we'll be doing today. So we'll start with a brief introduction about FEBio, the FEBio project itself, and then we'll jump right into FEBio Studio. We'll do a demo of the software for about 60 minutes. After that, we'll have a Q&A session. Now, you should be able to see your Q&A window, so you don't have to wait till the Q&A session if you have any questions that can't wait till then, or if you don't think you'll remember your question by then, feel free to enter it in the Q&A window. We have several panelists standing by for answering any urgent questions. And then after the Q&A session, we'll have a few concluding remarks. Okay, so let's get started. FEBio is a finite element solver that was designed specifically for solving problems in biomechanics and biophysics. It is a collaborative effort between the University of Utah, where it is led by Dr. Jeff Weiss, and Columbia University, where the PI is Dr. Gerard Atessian. The development of FEBio started around 2005 when we and other researchers in the field kind of felt there was a need for a finite element code that was specific to the biomechanics field. So at the time, people were often using commercial packages, which were, of course, not specifically geared towards biomechanics, and as a consequence, had often limitations. And so this forced, a lot of researchers to develop their own finite element codes, which is, of course, a very challenging project, and many of these codes never made it into the public domain. So with FEBio, we kind of wanted to fill this gap, and on the one hand, we wanted to provide a software package that was ready to use and rich in features that are relevant to the computational biomechanics. On the other hand, because we realized that at the time and still today, computational biomechanics is a rapidly evolving field, we wanted to make it relatively easy for users to implement new algorithms and new ideas. And so we did that by making the code open source, and also by adding a plugin framework where users can customize the code without actually having to change the main code itself. We also try to provide good documentation so users can see how the code works and how it actually does the things it does. And we try to provide good support. So we have a forum where people can ask questions. And we also have a mechanism for reporting bugs and features. So when we started around 2005, our main focus was structural mechanics, and we had some, what we called at the time, poor elastic capabilities. But since then, our code has grown quite a bit, and I just want to give you a brief overview of some of the key functionality. So you can model basically any physical scales, from cell and subcellular structures to tissue, organs, and whole body. FEBio is a multi-physics code in the true sense of the word. So, we started with a mechanics solver, but we added several different other physics solvers since then, including fluid and FSI capabilities. And many of these solvers can be combined in a single model. One of the challenges in biological or in modeling of biological tissues is that these tissues have often a very complex organization. And so we have quite a big library on constitutive models where users can model almost any aspect of biological tissues. So many of our solvers support both steady state or quasi-static and dynamic or transient solutions. We have many different kinds of boundary conditions and loading conditions, including contact formulations. We have mass transport across contact interfaces and much more. So this is all great, but of course, the big question is FEBio being used by the community? And so over the years, we've we try to keep track of some statistics that give us an indication that FEBio is indeed being used. So we currently have over 12,000 users registered on the FEBio website. There are about 60,000 downloads of the software, and that's just the FEBio software, not including the supporting software. We'll say a little bit more about that in a minute. We're aware of over 500 publications, including journal articles, book chapters, and dissertations. In fact, the complete list of these publications is available on the FEBio.org website if you're interested. And we also know that FEBio is being used as a teaching tool in many courses around the world. So where are FEBio, or where are researchers using FEBio? So they're using it in many different research fields, including soft tissue mechanics, tissue engineering, damage modeling, joint and muscle mechanics, cardiovascular mechanics, angiogenesis, multi-skill modeling, modeling of vision and hearing, and much more. Again, a more complete list of all these publications and research areas can be found on the website. There are also several other tools that use FEBio, tools that are geared towards the biomechanics community as well. So for instance, there's the Gibbon toolbox, which is the MATLAB add-on that offers a lot of image and geometry processing tools. And they also allow users to export models as FEBio files. They can run the models in FEBio and then load the results back into MATLAB. There's also the surrogate contact modeling toolbox, which you can find on SimTK. So this toolbox uses FEBio to essentially build a library of surrogate models. And then there's also the Open Knees project, which aims at providing three-dimensional, fully detailed knee models. And they distribute these models as FEBio input files. So I think this kind of gives you an idea of where and how FEBio is used in the community. And of course, we use FEBio as well. We not only develop it, but it's been used in several of our research projects as well. So as I mentioned, FEBio is a collaboration between the University of Utah and Columbia University. So on the Utah side, FEBio is used in a couple of different projects. So there's a project that focuses on hip joint mechanics, or more specifically, the mechanics of cartilage, both in healthy tissue and damaged tissues. There's also an angiogenesis project. So angiogenesis is the formation of new blood vessels. And this is kind of an interesting project because the angiogenesis part, at least the simulation of these blood vessel growth, is a separate library. It's a separate code, and it's linked to FEBio through the plugin framework. And so that allows this code to be used in FEBio, where you can use it to look at the effects of angiogenesis on tissue mechanics. And then a relatively new project that we've started involves around characterization and visualization of complex fiber distributions. So as you know, biological tissue is often very fibrous. We have very complex fiber organizations. And so there are some challenges. How do you characterize that, not only in the reference state, but also as the model deforms? And there are also some challenges with how do you represent that visually? And so that's a project that also uses FEBio to sort out these things. On the Columbia side, there's also great interest in cartilage mechanics. So they use both experimental and computational methods for studying the mechanical properties of cartilage. But they've also done a lot of fundamental theoretical work, and much of that work is based on mixture theory. And so all these theoretical developments that they developed are available in FEBio. And so that includes not only the biphasic and multiphasic code, but also a novel fluid mechanics solver, which is also coupled through our mechanics solver, which allows you to do FSI. Okay, so one important thing to know is that FEBio is a command line solver. That means if you want to run FEBio, you have to open up a command window or a shell window and pass it an input file. FEBio will then run, and then produce an output file. So in order to make FEBio easier to use, we also developed our own preprocessor and postprocessor. And these were these supporting applications that I mentioned earlier. So they used to be separate, but recently we integrated these applications into a single environment, which we call FEBio Studio. And FEBio Studio is going to be the focus of the demo. So in FEBio Studio, users can build, run, visualize, and analyze their FE models. So before we get started with the demo, I thought it might be helpful to give a bit of a general overview of what a typical workflow with FEBio Studio looks like. So usually users already have some meshes. They come from, for instance, from image segmentation. And so usually they have some kind of surface or volume representation already. So they would the first step would be to bring that into FEBio Studio. In the case of a surface mesh, you can then create volumetric meshes. In the case of a volume mesh, you can remesh if necessary. So once the mesh and the geometry have been defined, it's time to add all the physics. That includes adding all materials, boundary conditions, contacts, and so forth. Once the physics has been set up, you can call FEBio. And so FEBio Studio will do this for you, as we'll show later. So this process is fairly transparent, but FEBio still does all the work in the background. And then once it's completed, the results can be brought back into FEBio Studio, where you can then do any kind of visualization or analysis. Okay, so let's get started with our demo. So I'm going to open FEBio Studio here. So by the way, this version of FEBio Studio will be made available after this webinar. So the current version online is the 1.1. This is the 1.2, even though it says 1.1 here. So we'll update that and upload this version later after the webinar. All right, so when you start FEBio Studio, it looks like there's someone who wants to answer a question live.
Sorry about that, Steve.
No worries, no worries. Okay, so when we start FEBio, you're greeted by the welcome panel here, the welcome screen. And so the welcome screen just offers you some shortcuts to starting a new model or opening an existing model. There's also a list of recently opened models. And so what we're going to do, however, is we're going to look at the repository panel. So I just lost my mouse. Where is it? There we go. Okay, so the repository panel is a panel that gives you access to an online database of models that are shared by the community. So if you have an account on febio.org, you can log in here with the same credentials and add your own projects if you want to. Or if you just want to download a project, you can just browse through this online database and look at some of the models that we have here. So what we're going to do actually is kind of a simplified version of this project here, which was a part of a PhD work of one of Jeff's students. So as you can see here, not only are these the models that are part of that publication, you can also see the publication itself. There's even a DOI link that will take you right to the publication if you are interested. Now we're not going to do these full models. These are pretty big and may run pretty long. Instead, I've created a simplified version, and it is also available through this repository panel under the tutorials and then webinar intro to FEBio Studio. So there's two files there. There is the blank model, which we're going to start with. But if you want to see the completed model without going through all the steps that we're going through, then you can just open up the completed model and run that straight away. So like I said, we'll start with the the blank model. Okay, so I had it already downloaded, but if you hadn't downloaded it, then FEBio Studio will download it from the database for you and then open it up in FEBio Studio. Okay, good. All right, so what we're gonna do basically is this represents a simplified version of a hip joint, right? So the bottom part here will represent the cartilage layer on top of the femur. And then the top part here represents the cartilage layer on the acetabulum, so the cartilage layer inside the hip socket. And then this ring around it represents the labrum. So what we're going to try to simulate here is we're going to simulate a very simple gait analysis. So we're going to prescribe some kinematics to the femur, the underlying femur, set up a gait analysis, all their boundary conditions and so forth, and then run this in FEBio Studio. So I want to emphasize that we're not going for physical realism here. So this is just a model a simplified model to kind of show you how things work. If you want to see the more realistic model, then you can go to that paper that I just showed you on the repository panel. Okay, so let's get started. The first thing we're going to do is create some material parameters. So we'll start with the femoral labrum, the femoral cartilage. So I'm going to hide the other parts for now, and I can hide them by selecting them and then clicking the H shortcut key. So for this model, we're going to use a very simple constitutive model here. So I opened up the material panel here, which allows you to select all the different materials. So I mentioned earlier, we have this really big library of materials available. And so as you can see, these are some of the materials. So there's different categories, and each of these categories has a list of different materials. So we're just gonna pick a simple neo-Hookean material. If you forgot what this particular material does, you can click on the help button here and it'll open up the corresponding help page. So this is the same page that lives on the user manual, but it pops it up here conveniently so that you can look at what the parameters were, what the constitutive formulation was, and so forth. Okay, so we'll pick that. Now, one of the common problems that people run into is that they want to prescribe heterogeneous material parameters. So they want to prescribe materials that essentially depend on the position of the nodes and the elements. So there's a couple ways you can do that. And one of the ways you can do it is by entering mathematical expressions. Right? So if you go to the model panel here, so I'm on a model panel, which gives me an overview of all the components of the model. And then below in the properties panel, you can enter the material parameters. So if you set that to math, you can enter any kind of mathematical equation. Now, what we're going to do actually is we're going to create a map. So to create a map, we have a tool in FEBio Studio that allows you to do that. And so to find it, go to the build panel. On the build panel, click on the tools panel, and then find the scalar field tool. So the way this is going to work, this tool, is basically you're going to assign values to different selections. And then after you've done that, you'll click on Create. FEBio Studio will then kind of interpolate all the data that you've entered to find the values on the entire mesh. So what I want to do here is I want to make a map that assigns a Young's modulus of 1 on the inside surface, and then a modulus of 2 on the outside surface. And then again, FEBio Studio will interpolate between the two surfaces. So how do I do that? Well, I have to select the inside surface first, and I can do that by clicking here on the face selection button. If I then click on the inside surface, you'll see that a region is selected here, and the region that's selected here is based on this angle criteria here, and I can increase my selection by just shift clicking, or if I press Control+, I can simply just grow my selection to the boundary. Okay, so on this inside surface, we'll assign a value of 1. Now we'll do the same on the outside surface. So we'll click, and I'm just going to grow my selection till it reaches the boundary. Okay, and on that side, I'm going to assign a value of 2. Let's give this a name. We'll call that EMAP. These parameters are control parameters for the algorithm that finds the interpolation between all these values. So we'll just leave these for default. And then we've added our data map successfully. So how can we see the result? Well, to see the result, we go to the mesh inspector here. So the mesh inspector allows you to look at various measures over the mesh. So you can look at volume, Jacobian, quality, some quality measures. And we'll come back to these in a minute. We're looking at some tetrahedral meshes. And at the bottom is the map that we created. Okay, so you can see here that we have indeed a transition from roughly 1 to roughly 2. It's not exactly 1 and 2 because the values 1 and 2 were the values at the actual surfaces. But because we need to have these values at the elements, it did a little bit of interpolation to generate a single value, a constant value for each element. Okay, so now we can assign that mesh. Go back to the model panel, assign that map, I mean. So the map shows up here under mesh data. So this tells you that we have a map created, and we can assign that map here by just selecting the map option and then typing the name of the map. For the Poissons trace here, we'll just do a single 0.3 value. Okay, so we still need to assign this material to this mesh, and we do that simply by clicking the plus icon here. So this will add whatever you have selected in your graphics view and assign that to that material. So you'll see now that the object has the same color that was assigned to the material. If you want, you can change these colors like that. Okay, so that's the femoral cartilage. In fact, let me call this F-cart so we know what is what. Let me go ahead and unhide the other part here. So the other part consists, or the other object consists of 2 parts. We have the acetabulum cartilage, and then we have the labrum. So we're going to use 2 materials to describe these different parts. So I'm going to start by hiding our femoral cartilage. For the acetabulum or the pelvic, we're just going to use a simple neo-hooking material. Because I want to focus more on the labrum part. So because this consists of 2 parts, I have to decide which part I want to select. So you can do that by selecting here the part selection tool on the main toolbar. And then once we have that part selected, we assign that to that material. And so I have 2 yellows, so I'm going to make this one back to orange. Okay. So next, the labrum part. So the labrum is, a tissue that has a lot of fibers in it. So we're going to use a different material. We're going to use a coupled trans-iso-munirivlin. And so what makes this material is somewhat different is that it allows you to specify a fiber direction. So let me first assign this material to the labrum. Okay. And so let's talk a little bit more about these fiber directions, because this is something that people often need to do when they're dealing with biological tissues. There's quite a few methods to describe fiber orientations. But before I do that, let me first actually show them. So I right-clicked here on my graphics view to get up this, to pop up this context menu. Then I can toggle the fibers on. So the fibers are color-coded based on the XYZ coordinates here. So in other words, you can kind of see this little triad here, which has a red X arrow. So if you see a red fiber, that means it's pointing in the X direction. Okay, so let's look at a few different options we can set these fiber directions. There are a few different procedural methods that are implemented that simply allows you to create fiber distributions based on some parameters. So we can create cylindrical distributions by specifying the center, the axis, and then the initial fiber direction. So we have a couple more. We have spherical. We have angles where you can specify the spherical angles of the fibers. But the one we're going to use here is user. So the user is just going to be a fiber that depends on a map. So we need to create another map. This time we'll have to create a vector map. And we have another tool for that on our build panel. If I can find my mouse, there we go. Okay. So under the scalar field, there is a fiber generator option. And this fiber generator option works very similar to the scalar field. So basically you assign values at different selections. FEBio Studio will interpolate these values, so that will create a scalar field. And in order to get the vectors, it takes the gradient of that scalar field. So in this case, what I want to do is I want to create a fiber field that kind of follows along the circumference of the labrum. So let me start by first hiding the pelvis so we can, the cartilage on the pelvis. So we have a clear view of the labrum. I'm going to change the color as well because that purple is going to interfere. Okay. So the way what I'm going to do now is I'm going to assign some values on some selection, a node selection. So let me zoom in here a little bit so I can select these individual nodes. Oh, missed one. Okay. And on these nodes, I will set the value 0. On the opposite side, I will select these nodes. It looks like I got them all. So I'll assign the value of 1. Okay, so once we click apply, so FEBio Studio will interpolate on the rest of the mesh and takes the gradient. So in this case, I'm going to change this parameter here. You can also limit to which material. This is actually somewhat important because we only want to generate these fibers on material 3, which was the labrum. Okay, so let's apply. And it looks like that worked. So again, the fibers are color coded. So where they are red, they're pointing along the X direction. Where they are green, they are pointing along the Y direction. Okay, so let's turn off the fibers. Let's go back to our model and unhide everything. I forgot to rename these materials, so let me do that now. So this is the P card, and this will be the labrum. Okay, the next thing that we have to do is think about boundary conditions. So what we're going to do is we're going to basically provide or prescribe some kinematics to the femur, which we don't have in this model yet. Okay, now in principle, we don't really need a geometry when we're dealing with rigid bodies, but it is often helpful to kind of see what's going on. And it also allows me to show a few different things here in FEBio Studio. So we're going to create some geometry for the femur and then import it in this model. Okay, so I'm going to start by creating a new model. And it looks like this window here pops on the other screen. So it doesn't really matter what we're going to do here, but just to show you, if you start a new model, you have the option to select a template. And what this basically going to do is it's going to populate the menu items based on your selection here, and it will only show you the selections that are relevant for that particular type of analysis. So we'll just leave it at structural mechanics. All right, so what I'm going to do next is I'm going to grab a model of a femur, and this model is from the SimTK Grand Challenge data. So this is an STL file. And so in this case, I just dragged it and dropped it on the screen, but you can also go to File, Import, Geometry, and there you'll see all the different options that we have, including FEBio, obviously, there's Abacus and ANSYS, LSDyna, and so forth. So it's quite a list on different file formats that we support. So this is usually where people start. So they have some mesh that they want to bring in and do finite element analysis with. Now, usually you'll probably have to do some remeshing. So in this case, the mesh is quite fine. And if we do simulations on this, then we're going to create a very big finite element mesh. So what you can do is you can coarsen this mesh. So we have a few different tools that allows you to change the mesh. So you'll find these all on the build panel. In this case, on the edit panel here. So this was brought in as an editable surface. So that means that you can modify the surface mesh before you generate the finite element mesh. And that's exactly what we're going to do here. So in this case, we're just going to decimate the mesh a little bit. When we decimate the mesh, you basically just specify a scale factor of the number of facets. So in this case, we'll end up with about 10% of the original number of facets of this mesh. So we apply, and there you go. We have a coarser mesh. Now this is just a surface mesh. So in order to generate a volumetric mesh, we go to the mesh panel here. And so in this case, we want to create a tetrahedral mesh. So it uses the TETCHEN library on the back end to create the tetrahedral mesh. The default parameters are fine. So we just click apply. Of course, not much has changed. So how do you know you actually have a finite element mesh? Well, the mesh inspector is here to help. So when you click that button, it'll show you that you indeed have a 4-noded tetrahedral mesh. So, and as I mentioned before, you can look at various different quality measures. So for tetrahedral elements, you can look at the TET quality measure. In this case, lower is better, and the minimum is about 0.62. So this is actually a pretty good mesh. I would not have any concerns with this mesh if I want to use it in a finite element model. But just to show you, you do have the option to do a full remesh of this model. So on the mesh panel here, there is a TET remesh. And so this uses a different library. It uses the MMG library in the back end. And this library allows you to create an entire new tetrahedral mesh off an existing TET mesh. So, okay, there you go. It refined it a little bit. It was kind of hard to see. Maybe you can replay this in slow motion later to see the difference. But anyways, so we've created a mesh. If you want to, you can also, delete elements and move things around. In order to do that, you would convert this to an editable mesh. So now before I do that, I'm going to show you how to bring this model now into the other model. So this model, exists in a different, or this object lives in a different model. And so if I want to use this in my simulation here, so I could just write this to a file. I could go File, Export Geometry, and write it as any of the formats that are supported here. But in this case, we can also use a shortcut. We can just go Edit, Copy Object, and we paste it right in our model. Now, in this case, these geometries are in different coordinate systems. In fact, they have really nothing to do with each other. So we'll have to move this object a little bit to put it in the right place. You can move objects here by clicking any of these transform tools. So to click on the translate tool will allow you to move the object. You can also rotate the object and scale the object. Of course, doing this manually is of course tedious if you want to get it in the right place. So there's also a dialog box that allows you to enter values indirectly. And so let me just grab my cheat sheet here. So I'm just going to copy some values here. Sorry, this will take a second. Okay, so this is the displacement. So for the rotation, you can set the angles as well. So the angles are in degrees. Okay, so that was X. There's Y. And finally, the Z angle. And then we're also going to scale this a little bit. Okay, and so that puts the femur exactly where I wanted it. Now, just to show you that you can delete parts of this mesh here, we're going to select some elements. So I selected the element selection tool at the bottom here, and then I'm just going to use my shift drag to select all the elements on the bottom and delete those. And that'll make it a little bit easier to manage this femur here. Okay, so we have some geometry now for the femur. So let's talk about materials that we have to assign here. So because we want this to be a rigid body, we have to create a rigid body material. So again, we go to our material panel here. In this case, we click the other category and we select rigid body. So this is how you make a rigid body in FEBio Studio, or in FEBio, you just assign it a rigid body material. Okay, there are some properties here. Now, most of these properties are not going to be relevant for what we're doing here. The only thing we do care about is the center of mass, or in this case, the center of rotation. So we want to prescribe some rigid kinematics. We're actually going to prescribe rotation. So we want to make sure that we have the right center of rotation here. In this case, I want to have the center of rotation right in the center of this spherical mesh here. So let me start by hiding the femur for a second. So I want to be able to fit a sphere to this and find out what the center of that sphere is. And I can do that using the measure tool. So the measure tool is a nice little tool that allows you to measure very different kinds of metrics. So you can measure distances between nodes, angles between line segments. You can measure area, volumes, and you can also do a sphere fit, which is what we want to do here. So First, I'm going to select the inside surface here. And then check selection only and then fit. And so that fits a sphere directly to my selection. And this allows me to copy the center of that sphere into the material properties here. So there is the y coordinate. And then there's the z coordinate. Okay, so we have now our center of rotation defined. Let me show everything again. Okay, so the next step is setting up the kinematics here. So what we're gonna do is we're gonna apply this, this gait in basically 2 steps. So in the first step, we'll apply a load to the femur that kind of puts it in place and keeps it in place. And in the second step, we'll actually prescribe the kinematics. So let's get started by adding 2 steps here. So we'll create first the loading step. And then in the second step, we'll call that the gait step. There we go. So let's take a look at some of these properties here. So one of the important properties here is the time settings. So by default, a step will have 10 time steps, and each step size will be 0.1, right? So the simulation time will essentially go from 0 to 1. And so why do we, by default, set multiple time steps? Well, because it turns out that if you do large deformation analysis, it's often not possible to apply your load in a single step. Usually, FEBio will not find the right solution if you try to do that, and it's often a better strategy to increment your loads slowly over multiple time steps. So that's what we're going to do here. Okay, so let's start by adding the force that has to keep the femur in place. So all rigid constraints can be added here in the rigid constraints item by right-clicking on it and then select Add Rigid Constraint. So in this case, we just want to prescribe a force. We're going to apply this force to the initial step, and so that basically means that the load will be applied when the simulation starts, and it will remain applied during the entire simulation, including in the second step. So we'll pick here a z force, and the value will be 10. So I just mentioned that, usually you want to have multiple time steps so that you can ramp up the force. Well, so how do you actually do that? Because we just enter the value 10 here. Well, what happens actually in the background is that in many of the loading conditions and boundary conditions and constraints, there is also what we call a load curve associated with it. And so in order to see that load curve, you go to the curve editor, which is this little icon over here. So the curve editor also shows a model overview. In this case, it'll show you all the parts that have a load curve associated with it. An easier way to get to all the load curves is just using this filter dropdown and select load curves. So as you can see here, the default load curve that is applied is a simple linear ramp that goes from 0 to 1. So what's actually going to happen is that the actual force value that will be used at a particular time will be that 10 multiplied by the value of this load curve, right? So essentially what this means is that the force will ramp up from 0 to 10. Now there's a few different things we can do with the load curve here, but I'm going to show that once we talk about the rigid kinematics. Okay, so a rigid body has 6 degrees of freedom. In the first step, when we load this analysis, or when we load this femur, we don't want the object to rotate. So we're going to fix the rotational degrees of freedom, and we do that by adding another rigid constraint. So in this case, we only want to apply that in the loading phase. We're going to fix the displacement. So we check that, and then we select the X, Y, and Z displacements. Okay, so what's going to happen now in the first step is the force will be applied. The femur cannot rotate, but it can move, so it will kind of settle into the hip joint. In the second step, the gait step, we are going to prescribe the rotations of that femur. And the way we do that is we go again, we add rigid constraints. In this case, we select a prescribed rigid displacement. We want to apply that only in the gait step. And we select OK. So we'll select X rotation here, and we're going to set a value of 1 here. So there's also a load curve associated with this boundary condition. And so by setting the value to 1, we're essentially saying we're going to use the load curve to drive the X rotation. Okay, then we're going to do the same thing here for Y and Z. So we'll select gait till 4, prescribe rigid rotation. So Y rotation. And then the same for the Z rotation. Okay, let me double check here. Good. All right, so as I said, there's load curves associated with these 3 boundary conditions. So let's go back to the load curve editor. And so these are the 3 different load curves. Let me just give these a name so we can tell the difference. So this is the X rotation, Y rotation, Z rotation, and then this was the force. Okay, so it's a little bit easier to tell them apart. All right, so let's talk a little bit about these curves here. You can edit these curves, so you can edit them manually by inserting new points. So the way to insert new points is by just shift clicking on the curve editor. You can enter the coordinates of these points directly as well. You can move them around. You can change the interpolation type of these curves. So you can set it to linear or to step. So in this case, we'll just leave it to smooth. You can also generate curves based on mathematical expressions. So for example, let's say we want to sample a curve based on a sine. So we can do that easily. You can set the extent type, which basically means what's going to happen outside of this range that you specified. So this is useful for creating periodic functions. So in this case, we'll just leave it to the default value. So another way of generating curves is by digitally sampling images. And so in order to do that, you would right-click on the background here, and you would select a background image. So I just prepared the simple graph here. And unfortunately, it's kind of white background, which is not ideal, but you can kind of see the grids of the image on the background here. And so now the goal is to align the 2 grids. And so you can use that with this tool here. So when you select that, you can select the background rectangle. Again, it's probably impossible to see because it's a white background, but I selected the background here, and then I just have to enter the range. So for X goes from 1 to 2.2, and Y goes from 0 to 0.6. Okay, so that aligns the two grids, and now we can just start by digitally sampling this curve here. Oops, sorry. Align that. Okay, so we can just sample that curve back like that. Okay, so that's another way you can create load curves. A third way, perhaps the most convenient way when you're dealing with complex curves, is just load a file that has the data in there. So that's just a text file that has an X and a Y value separated by a space. Let me clear the background here, image. And so there you go. So you imported the curve from a text file. So that's what we'll do for the Y and the Z as well. So let's grab the Y file and then the Z file. Okay, so that defines the curve editors for the rotations. And I think we are then done with setting up all the physics that we're doing on time. Okay. Let me just double check here quickly if we set all the material parameters. Nope, I missed this one. Okay, so that looks good. Oh, we have forgot one more thing to do. In fact, quite an important thing. We haven't really connected all these pieces together yet. So the first thing we're going to do is fix the back of the acetabulum and the labrum to the pelvis. Now we don't have the model of the pelvis, but we assume it's fixed. So we have enough with just a fixed boundary condition. So I just select the back faces here. In my boundary conditions options, I select fixed displacement and then select X, Y, and Z. So that fixes that back part. Next, we have to attach the pelvic cartilage, sorry, the femoral cartilage to the rigid body. And we do that through a contact interface. So if you right click on that, we can select rigid contact interface. For the rigid material, we'll pick our material 4, which is the femur, and then we just have to say what part we have to assign. So we'll take the back part here, the inside surface of the femoral cartilage, and we simply assign that to the rigid constraint. Okay, so that has tied the femoral cartilage to the rigid body. Then the final thing we have to do is set up our contact interface between the two different cartilage layers. So the way we do that is we go back to contact, select contact interface. So we have a variety of different contact formulations, including different kinds of sliding interfaces, tight interfaces, and so forth. In this case, we'll just use the sliding elastic, which is usually the best one to start with if you want to do a sliding interface with or without friction. So in this case, we'll just do a frictionless surface. Okay, so what we now have to do is tell FEBio which surfaces are involved in this contact. So there are 2 surfaces involved. So it's the outside of the femoral cartilage here. So we'll assign that to the primary surface. And then for the secondary surface, what I want to show you is you can also assign facet selections to a contact interface. So in this case, we want to select the entire inside here of both the labrum and the acetabular cartilage. So in order to do that, so again, we click on the face selection tool here. We grow our selection to the boundary. So we assign that to the secondary, and then we'll also select the inside of the labrum here. So we can use that. We'll probably want to clean this up a little bit here, but fortunately, I already did that. So we have the inside surface here, and we'll assign that as well to the secondary surface. Okay, so let me make sure I have them all now. Yep. All right, so we've tied everything together. So the back here will be fixed. There's a contact interface defined between the 2 cartilage layers, and then the femoral cartilage is tied to the femur, to which we have prescribed some rigid kinematics. Okay, so let's talk now about running this model in FEBio. So the way to do that is you go to the Run FEBio dialog here. So you can give this job a name. We'll just call it job 1, so you can make as many jobs as you want. Then you have to select a launch configuration. So what a launch configuration is, it's basically whatever FEBio Studio needs to know in order to call FEBio. And so when you install FEBio Studio, there will be a version of FEBio installed with it, and it will usually be the latest version of FEBio. But if you have multiple versions of FEBio installed, you can customize these launch configurations. So there's different types of launch configurations. So the one by default is a local one, so the model will run locally, but you can also set up remote configurations, which will call FEBio on a different server. So in that case, you have a few more fields to fill out in order to make sure that FEBio Studio can find the FEBio executable, but it is possible to run FEBio on a server from within FEBio Studio. And then when FEBio is done on the server, FEBio Studio will pull in the data automatically back in. In this case, we're just going to run this model on our computer here. So I hope everything is done. We'll know very shortly. So just click run, see what happens. So FEBio is now running in the background. So this output here is generated by FEBio. So it kind of shows you what FEBio is doing. Looks like it is struggling a little bit. So it's so what you see here is the convergence norms of the Newton solver that FEBio uses to solve these models. So this is not going as smoothly as I expected it. Must have forgotten something. Okay, so you can stop the run by going back to FEBio and stop FEBio. So what I'm going to do here is I'm going back to my model here, repository panel, open the completed model and run that one instead. So by the way, all this output that is being generated here on the screen is saved is saved in a file. So I'll show you what's going on here. So when FEBio Studio runs, it'll first create the FEB input file. So you have that as well in case you want to run it again yourself through the external FE solver. So the log file is the file that you basically see here. So all the output that is being generated goes to the log file. And then this is the results file that FEBio Studio or FEBio is generating. And so once the run completes, then we can open that file and take a look at the results. So it has to go to time 2.0, so we're almost there. I think I forgot to change some of the step settings. Now that I think about it, that's probably why it wasn't running very well. So, but in any case, this version did run all the way. So we have a normal termination and we can now open the results here. So after you run a job in FEBio Studio, there will be this new jobs item that showed up in your model panel, and it has all the jobs that you ran. So you can open the results by just double clicking on that file. And so that brings us to the post-processing side of FEBio Studio. So it looks a little bit different. So we have here the post panel, which is open now by default, and it has a bit of an overview of what's going on in the model as well. So there is also the material tab, which shows us all the different materials that are in this part. And so what we can do here is we can hide certain materials that we don't want to look at. For example, you can change, how all these materials look. The data tab the data tab here shows all the data that was stored in the file and that FEBio Studio actually generated when it loaded that model. So the file contains only displacements, stresses, and some contact variables. And FEBio Studio added these additional fields. So the Lagrange strain measure was added because it noticed there was a displacement field, similar with position and initial position. And the pressure was added because it noticed the stress field. So the pressure is just the negative trace of the stress. So you can look at these fields by going here to the top bar and selecting any of these measures. So let's look at the stress, for instance. On the bottom here, you have your timeline. So your timeline allows you to navigate through all the different states or time steps that FEBio generated while solving this model. So you can also animate these results by clicking on the animate button here. So I'll just go through the different time steps. Of course, most of the action here is on the inside. So let's take a look at just the inside of the acetabulum by hiding the other parts here. Okay, so this will give us a clearer view on the inside of the model. We can look also at individual elements and nodes. And the way we do that is we click on the element selection button here, for instance. We select a couple elements, and then we can go to post, new graph, select some measure that we're interested in, and then it'll show you a graph of the results on those 3 different nodes. There's a few interesting tools here available as well. If you click on the tools panel, you can customize quite a few different things here in terms of what will be displayed on the graphs. You can change color options as well. You can also do some curve fitting. Now, this might not be the best example for a curve fit, but just to show that we do have these options available. So you can curve fit different kinds of curves here. And you can even overlay mathematical functions. For instance, probably have to scale this a little bit like that. You can store this graph too. So if you click on add to the model tree, it will add it here to the view. So you can save different graphs and reopen them later. So let's see what time is. Okay, we have a few more minutes. So let me show a couple more things here. So another way to look at the inside of the model is by hiding elements. So you can select a bunch of elements and then just hide them. So this will give you an inside view of what's going on in the model. Another way of doing the same thing is through a plane cut. So the plane cut cuts the mesh. Let me turn off the plane itself. So it cuts the mesh and gives you another way to look at the inside of the mesh. So you can change the position of where this cut is made as well as the orientation of the cut. So that's another convenient way of looking at the results on the inside of the mesh. So by the way, you can change how everything is being rendered here. So you can move all these little widgets around where you want them. You can change the color maps that are being used to show these results. You can even customize these color maps themselves. So if you go, for instance, to Tools, Options, Color Map here. So here you have all the list of color maps, and you can customize these color maps. You can set a default one if you like one of them. I think I have the hot cold set as the default. So when FEBio Studio starts, you'll always use that one as the default color map. So you can also make screenshots and video recordings of your model. And the way you would do that is go to record. So let's make a quick video recording here. So we click on record, click on new. Oh, actually, before I do that, I have to turn on the capture screen. So the capture screen is basically the part of the screen that is going to be captured when it creates this video. And by double clicking on the border, you can set the position and the dimensions of this video. So let's just pick that. So as I said, you kind of move these things around to get them where you want. So now let's go ahead and create a quick recording. Okay, so now we're starting in the stop mode. So let's just go ahead and start the recording. So from now on, everything I do will be recorded to this video. Now you might wonder why we have this feature, because you can just use any kind of external third-party screen capturing software. But one of the problems you'll have if you do that is that, especially when you're dealing with big models, is that FEBio Studio cannot render this very fast. You can only get like maybe 5 frames per second. So when you're using a third-party software, you're just recapturing that very slow animation. So what's happening here, on the other hand, it's taking every time it re-renders the screen and grabs all these frames and puts them in the video, so that the video will always be a very nice and smooth animation. Okay, so let me stop that. And then let's see what it looks like. Open with VLC. There we go. Oh, it's on the other screen. Okay, there you go. Okay, so that's how we would make a video animation in FEBio Studio. Okay, so let's take a look at the time. All right, so I think at this point, we'll switch to the Q&A session. It looks like there's been a lot of questions already answered. Let me take a quick look here and see what questions we can answer here. There are no open questions. Okay.
Steve, there's one question about list of shortcuts for selecting the mesh.
Selecting the mesh, what do you mean by that?
It says, what is the shortcut for selecting the meshes on the surface? I guess that means maybe the facets of the surface or nodes or elements on a surface. Maybe you could, were there keyboard shortcuts or other things that you were utilizing during the demo that you could clarify?
Okay, sure. So, so I got the mesh selected here. Once I have the mesh selected, I have these tools available to select individual items. So let me change the color here. That purple is not helping. So there's a couple different options here that affect what will be selected. So if I don't have any of these options available, and if I click on a facet, it'll just select that facet. So if I shift click, I can grow my selection. I can add, so it'll keep everything I have selected. If I turn on the connection, the select connected feature, excuse me, it'll select all the facets that have a normal that is that differs in an angle of 30 degrees or less of the facet I have selected, if that makes sense. So I can grow my selection that way much more quickly. I can grow it even faster by using a Control+ shortcut key, which will just grow it to the nearest boundary. I can also shrink it by Control-. By the way, these shortcuts are listed here under more selection options. So if you go to edit, more selection option, there is grow selection and shrink selection. So I hope that answers that question. Is it possible to import a complex scalar field from a file? Not yet. So, well, there is and there isn't. So you can write the file to the FEBio format. So if you can format it such that it looks like an FEBio format, then you can bring it into FEBio Studio. So that would be one way to bring in a custom scalar field from a file. How do you input bone growth algorithm? I'm not sure what that refers to. We have different material models that can be used for simulating growth. So I would suggest.
I think this question is about bone adaptation, whereby bone density, for instance, evolves based on specific mechanical variables. And Professor Ateshian has published a manuscript on that shows how to do interstitial growth and remodeling using the multiphasic capabilities in FEBio. So yes, you can do bone growth and bone adaptation within FEBio without having to write any code yourself. And I'd suggest that you look for the paper on our webpage that search for multiphasic and FEBio on the FEBio publications page. That should get it to you.
Okay, let's take a look at another question here. Can FEBio optimize parameters from two independent experiments at the same time? Not yet, but this is something that we know several users have asked, and I don't think it will be too difficult to add that. So I think this is something that we can address in the very near future. You probably maybe email me with a specific question so it stays on my radar, but that's definitely something that we'll be adding in the near future. Would you recommend applying a rigid body force for load-driven simulation or a surface loads? So that's a good question, and it kind of depends on what you're trying to do. So when you apply the rigid body force, it is applied to the center of mass, right? So it will not apply any torque. You can prescribe torques separately through another rigid constraint. So if you know the decomposition of your net force into force and moment, then I would recommend applying it, just using it that way. But for more general loads, the surface load might be the better way to go. So this user has an additional question about the open knee model. Do you know how to apply a force to a joint, not to the rigid body? So I think some of our rigid joints, and let me double check here. So if you go to, so the joints are under the rigid connectors. And I think some of these do allow you to apply a force or a moment. So let's see here. This one has a prescribed force here. I don't know if you can see where I'm pointing with my cursor, but you can apply the force or a moment directly to a joint. So yes, so that would be possible. Let me take a look at some other ones. Is it possible to change properties of a material in the middle of a simulation? So there's not much you can do once the simulation has started. So there are some ways to change things like the time step that is being used. If you run FEBio on a shell window or command prompt, you can do Control-C to interrupt the run. And so you have a few options to change things, but you cannot change the material parameters in the middle of a simulation. So you can make material parameters time dependent. So if you know in advance what kind of time dependency you want in your material parameters, then you can do that by assigning load curves to material properties. So any material, let me just show you here quickly. So to any material property, or most material properties, I should say, you can assign load curves as well. So for instance, the Poissons ratio here. So I could create a curve for the Poissons ratio. And so that value will now change as a function of time when you run the simulation. Is there any information or tutorials available based around sticky contacts? So sticky contact is a variation of the tight contact interface, and we don't have a tutorial specific on sticky contact, but if you go to the repository panel, where's my mouse here? So there's this test suite here, and so the test suite contains, I think over 300 problems that illustrate various parts of FEBio features, and under contact, you can find several several problems that use tight interfaces. So you can take a look. You can search for specific types of contact that you're interested in. In fact, let's just see if we have a sticky. Okay, so it looks like, I'm not sure what happened here because these are definitely not all sticky contact problems, but maybe take a look at those and then you can see how that's being used.
Steve, if you want to just limit yourself to sticky contact problems, you'll need to filter by file, not just project like you're doing.
And so how do I do that?
I think it's file colon. Either that or files colon. Try files colon, sorry. There you go.
Okay, there you go. So we have 3 problems that use the sticky contact interface. Regarding the HDO model, I assume that means the Holzapfel-Ogden model. Is it actually possible to describe fibers' dispersion around their orientation? So we don't have like a dispersion parameter in there, although some users have been asking for that. So this might be something that we'll be looking into. But as an alternative, we do have continuous fiber distribution, so you can prescribe, like for instance, an elliptical fiber distribution that I think will probably get you somewhat of a similar result as using fiber dispersion parameters. But again, as I said, since a few users have been asking about that, this is probably something we'll be looking at as well in the near future. Is there a way to place a plane cut to only a specific part, not the whole model? So yes. So most of these plots here, well, let me see where it is. Under material, you can choose which material that you want to clip. I guess I should pick one I'm actually looking at. Okay, so this would, so if you go to the material panel here on the post panel and you set the clip to no, then that material will not be clipped by the plane cut. Is it possible to include both the contact boundary and, when the surfaces are not in contact, a depth-dependent pressure? So the pressure is a boundary condition that you can prescribe via a mathematical equation. So you can, in that sense, prescribe a pressure that depends on you know, on the position or the depth. I'm not sure if that's what you're referring to, but but I guess yes. If that's what you mean, then yeah, you can prescribe the pressure as a function of the position, and in that case, get a depth-dependent pressure. Are you planning to add export as 3D PDF file or other similar file types that could be used for journal publications? So I have looked at the 3D PDF file format, but unfortunately it was quite complex. So it's probably not something we'll do recently unless we find a library that can basically do the conversion for us. We're doing on time here. Okay, maybe I'll try to answer one or two more questions. So this user asks, is it possible to modify the FEBio input file so that a specific subset of results are automatically written into a text file after the simulation is over? So you can write data directly to a text file, and you can even define which element sets or node sets that you want that data for. So I didn't talk about this, but you have these output options here. So there's the plot file option that tells what FEBio will store in the plot file. And then there's the log file, which will tell FEBio to generate any additional data. So the data will either go in the log file, or you can even have it go to a separate text file. So that is possible, but you will have to set that up in advance. Okay, someone's asking me, will these kinds of webinars be a frequent thing? And the answer is that we hope so. We hope to be doing this more in the future. We don't have any plans for a second webinar yet, but I'm pretty sure that this will become more of a thing in the future. We're also planning on creating video tutorials that we will make available on our FEBio site as well. So you can definitely expect to see more of us in the future. Okay, so I think we're going to leave it here with the question and answers. And so let me go back to my webinar. I apologize, I didn't get through all the questions here. So if we know who the attendee, it looks like we know who the people are. So we'll try to reply to these people, the rest of the questions via email. Okay, so let me wrap up quickly here by saying a few concluding remarks. So first of all, I want to say thanks to the FEBio team, to all my colleagues, many of which have also been panelists today. So thanks for being here. And then also, of course, want to acknowledge our funding sources through the NIH, who've been very generous with funding all of this FEBio work over many years, more than a decade at this point. If you want to know more about FEBio, I would say the place to be is www.febio.org. So that's the main website. You'll find there all the software downloads. You'll find there also all the manuals, so the theory and the user manuals, as well as some tutorials and case studies. So all of this will be available on the knowledge page. So if you click on the knowledge page tab, you'll find all this information. If you click on the support tab, there is a link to our forum. So our forum is hosted on a separate website, but you can find the link to that website on the support page. If you want to get in touch with us, I'd say the forum is probably the best place to go, but you can also reach us via email at info@febio.org. And then our source code is, of course, it's all open source, so it's available on GitHub. We also have a Twitter account if you want to stay up to date on news. So just look for the Twitter handle at FEBio Software. And then we also have a YouTube channel where we post FEBio videos. And in fact, okay, so yeah, so you can find these videos there as well. And so let me conclude by saying thank you to all the attendees who've watched this webinar. So I hope that you found it helpful and informative, and we hope to see you again in the future. So thanks and have a good weekend. Bye.
Thanks for coming. Appreciate it. See you soon.